This is still topic 2C about interbonding, and we're going to look at Lewis structures. So Lewis structures of covalently bonded molecules. Lewis structures use dots to represent valence electrons in atoms when they form molecules. When atoms form molecules, they share electrons to achieve full s and p subshells. In the case of hydrogen, this is 2, a duet. In the case of the second period nonmetal elements, this is 8, or an octet rule. So most elements want to have 8. Hydrogen wants to have 2. Some elements in the third period can have more than 8 electrons in their outer shells because of the expanded octet rule, because of their d orbitals, just so you know. So this is how I draw Lewis structures. There are other ways to do it. I find this to be the simplest way to do it. It doesn't work all the time, especially if you have an expanded octet item going on, but you can pretty much figure that out once you get the basics down. So what I do is I take the perfect number of valence electrons each atom in a compound should have, and that's almost always 8, except for hydrogen is 2 and boron is 6. And then you'll minus the actual number of valence electrons that they have, and those you just look at the periodic table and it's the group that they're in, and then you divide by 2. So again, it's the perfect number of valence electrons added up for the compound, minus or subtract the actual number of valence electrons for that compound, and you divide it by 2. And the resulting number is the number of bonds between the center atom and the atoms attached to the center. And usually the single thing is the one that goes in the center, but that's not always the case. Sometimes you've done this long enough to know which one goes in the middle. So then you will place the extra electrons you have on the center atom or on the atoms attached to the center atom. And these electrons, the actual number that you calculated up here, must add up to all the electrons you have present after you've drawn this figure. So where the perfect valence the perfect valence electrons equals the number of electrons the atom would like to attain, and then the actual is what it really has. For example, let's do water. So if water were perfect, each hydrogen would have 2. So 2 times 2 is 4. And if oxygen were perfect, it would have 8. So 8 plus the 2 is 12. That's where the number 12 comes from. Now we're going to subtract what it actually has. Each hydrogen actually has 1. So 1 plus 1 is 2. And oxygen actually has 6. So 6 plus 1 adds up to 8. So 12 minus 8 is 4. Now, if this number is odd, you did something wrong somewhere. And then 4 divided by 2 would be 2 bonds. So for water, oxygen is the center, and then each hydrogen is attached by a single bond, and each single bond would add up to 2 bonds. And then you actually have 8 electrons. And so you need to have your electrons, that's a groovy H, isn't it? Add up to 8. So each of these hydrogens is satisfied, so to speak. That hydrogen is sharing 2 electrons, and that hydrogen is sharing 2 electrons. But the oxygen is not quite finished yet. The oxygen has 2 there and 2 there, which is 4, but then it needs 6 and it needs 8. So if I could undo that, so you have your oxygen in the middle, each hydrogen doesn't quite look like that. And then it has to add up to 8. So 2, 4, 6, 8. So there's another method for drawing the Lewis structures. I'll let you read through that one. I'm not as comfortable with that method. So VSEPR, valence shell electron pair repulsion. This is really just talking about the shapes of the compounds. And you have to be able to predict these shapes and the angles. So the shapes of the covalently bonded molecules and ions can be determined by considering the number of electron pairs around the central atom. The electron pairs repel one another and try to get as far apart as possible. This theory is called VSEPR, valence shell electron. There are some standard shapes for specific numbers of electron pairs, and some simple deviations from this theory with non-bonding lone pairs are present around the central atom. Those shapes, their names, bond angles, and other relevant information are listed on a table on another page. So non-bonding pair will repel more strongly than a bonding pair. So when comparing bond angles, it can be seen that this has the effect of altering the bond angles and the shape of the molecules that have similar total number of electron pairs around the central atom, but where the total is made up of different combinations of bonding and lone pairs. I've seen many questions on AP exams on the free response part asking or stating why in this compound is the angle this, and in that other one the angle is this, and it goes to the lone pairs and repulsion, and if something's repelling it's probably making a larger angle. So for the purposes of predicting shape, multiple bonds can be considered as single bonds or single negative centers. For example, a double bond is considered just to be one bonding pair when predicting shape, and carbon dioxide can be considered to be surrounded by two electron pairs, negative centers, and is therefore linear even though there are actually two bonding pairs on either side of the carbon atom. That was kind of a sidetrack there. So predicting shape. You got to draw the Lewis structure. Count the electron pairs, both bonding and non-bonding, around the central atom. Use the table to recall the correct shape, name, and bond angles that correspond to the shape that arranges and minimizes repulsion. Keep them as far apart as possible. There is not a nice table on the test, though. You have to have this in your head. So here is a very, very thorough one. This is the one that we had in first year chemistry, and it doesn't cover all of it, but it'll help you as a basis, and then you add on to it. And again, we had the linear that we talked about in another screencast. 180 degrees. If you just have two atoms, it's linear. Sometimes, though, you'll have, like carbon dioxide, two atoms attached to the center and no lone pairs. It would be 180 degrees. It would be linear. There's trigonal planar. There's two types of bent. There's one type of tetrahedral, and there's a trigonal pyramidal. But if we go and look at this, you can see there's so much more. So we got the linear, the trigonal planar, the bent. It's also called the V-shaped. Tetrahedral, trigonal pyramidal. We talked about those ones. Now this one here, look at that. We never talked about this. And in fact, I just told you all these angles were 110. And look at them. They're actually a little bit different. Stinkers. So here's a tetrahedral that is bent or V-shaped, and it has that angle. And here's a trigonal bipyramidal. We never talked about trigonal bipyramidal. We never talked about seesaw or T-shaped. We never talked about octahedral or square pyramidal or square planar. So first year chemistry, apparently we got off extremely easy. So resonance structures and bond length. Occasionally when drawing a Lewis structure that involves multiple bonds, it may be possible to draw a number of different but still feasible Lewis structures. So in such a case, we call the various structures resonance structures. For example, carbon dioxide has three possible Lewis structures. You could have 3 and 1. You could have 3 and 1. That is a different oxygen, so that represents something different. Or you could have 2 and 2. And this changes how many lone pair electrons are on the terminal oxygens. It doesn't change the lone pairs on the carbons. So the carbonate ion is another example. So you could have a double bond there, you could rotate it there, or it could be rotated there. And remember when you're drawing these for ions that you have to put these brackets around it, and the charge goes on the upper right-hand corner. So the reality is that the structure is an average of all three possible resonance structures, and each bond is really 1 1/3 covalent bonds, rather than any combination of two singles and one double. So if a multiple bond, double or triple, is created between two atoms, the bond length observed will be shorter than the corresponding single bond. This is because a double bond is stronger than a single bond and hence pulls the atoms closer together. So a triple bond is correspondingly shorter and stronger than a double bond. Evidence for the 1 1/3 bond order in the carbonate ion is that all the bonds are found to be the same length, not the different lengths that you would expect. And so those are the end of our notes for this part of topic 2C. Next time we'll meet up and finish topic 2C. Until then, atom up.